All right, let's see. Is everybody ready? Only one student? Only Steven is having the camera on? You guys like my picture, huh? I was like, I wish I were at the beach. That's what it's about. Anyhow, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, okay. Emily, you are our lucky number 10 today. But before we get to Emily, was Alan the lucky winner last time that we didn't get around to? Is that right? Okay. All right. Let's just what happened to Emily? I don't know. Epic. Oh, Emily is part of the Epic Club. Good for you. Okay. Now, Alan, you ready to go? The second portion of actually finished up chapter 22. Is that right? Oh boy. You all right, Emily? Did the lucky number 10 really hit you that hard, or you got your blankets and everything? Hoodies. It looks like we're in different season. Are you okay? You're not, are you sick? No? I'm ready to go to the beach. You're ready to go, well, spend like the winter days. Oh boy. All right, Alan, you ready? You want to start it us off?
Yeah, can you hear me?
Okay.
I put D for 9.
You know which number are we doing?
No, is it 9?
Uh, I wanted to say it's A, but let me double check. Let me double check. Nine, yeah. Number 9.
I put D.
Excuse me?
I put D.
Can you say a little louder? I can barely hear you.
I put D.
Okay. All right. D is correct.
Yeah.
What's the reason for that?
I think it's something to do with like Lenz's law. Yeah.
Okay, can you give us a little bit more detail? How you approach this one?
I don't remember. I'm not really sure what I did.
Okay, how are you gonna use your right hand rule here? When the switch is closed, what happened? Hmm? Anyone else want to help out? Anyone? Where's Alan? Alan is okay. No explanation, just a lucky guess. All right, I'm gonna go by my screen order. Steven, what did you get? Did you get D as well?
Yeah, I got D as well.
Okay. What is your approach?
Um,
Mhm.
I'm not really sure. I sort of guessed it.
Okay. Boy, you guys are all lucky. It's not easy to guess it right. You got what? A, B, C, D, right? So what happened when you close the switch? Pick another one. Victoria, you Lex. What do you think? D is correct answer. Yes. But what is the reason behind it? Hmm?
Um, is it because the induced current flows the opposite direction from the original flux?
The induced current flows in such a direction that it will create an induced field opposing the growth from the larger coil, right? Therefore, the induced field is which direction is it going to be going?
Clockwise?
The induced field is supposed to be away from you, right? Into the screen. Is that right? We're talking about the magnetic field. We're not talking about the current yet.
Oh,
So if you use the right hand rule, then you can say the induced current is flowing clockwise. Everybody agree on that? Okay. And then what happened? Why only, you know, exists for a short period of time? That's because when the larger coil started out, it's going to be reaching from 0 to its whatever the equilibrium value is going to be, right? Once the larger one reaches the equilibrium value, then what do we know? Then the field causing by the larger coil is not changing anymore, right? So if the influx is not changing, then that means the induced current is going to be dropping back to 0, right? Because that has everything to do, or say that relates to the influx change, right? So since the larger coil is not changing anymore, then we know the induced current is a small one. It has to be 0 again, right? Does that make sense? Is everybody clear on that? All right. Who is Lex? Number 10. Number 10 is gonna be what? Hold on. Where? Emily. You're number 10.
Okay.
And then you're gonna do number 10 too.
Number 10, I got B.
B, are you sure?
Yes,
Are you absolutely sure?
100%
I'll give you a second chance. Answer that again.
B.
Okay, all right, yeah. B is the right answer. All right. So you got to perform under pressure, right? So good. All right, B is the right answer. Now, what's the reason behind that?
I don't know, like B has a larger area or something, I think. Yeah, B has I mean, no, not B has a larger area. Cause like if they all have the same like
Correct. They have the same lens, okay.
and then if you like form shapes, circle would have like the biggest area, and then the rectangle would have the smallest.
Okay, everybody else agree on that? Everybody else get B as well? Okay, so the peak EMF is always proportional to the area of the coil, right? So we need to figure out of all these options, what is the area, right? We can figure out what is the area of the square, what is the area of the circle, what is the area of the rectangle, right? And we can figure out, the area of the circle is going to be the largest, right? Is that how everybody else did? Right, because you have the same area square divided by 4 pi. And for square, rectangle is what? L squared divided by 16, L squared divided by 18, so on and so forth. So, circle has to be the largest, right? 4 times 5, that's, yeah, 3.14, yeah, 12 something, right? So that's how we got this one. Okay, any questions on this? All right, number 12. So who we got? We have Helen. Helen is up next.
I was kind of confused.
For
Like, I know the answer is D because I was searching it up, and then I don't understand what the answer is talking about.
All right, let's take a look. That's 12, right? Okay, who is next? William, you want to help out? How did you do your number 12?
I wasn't sure, so I also had to search it up, but I also didn't understand the explanation.
Okay, Jessica, batting third.
I looked it up also.
Uh-oh, we got 3 strikeouts. Ivy, you Lex.
I'm not too sure.
Ooh, my goodness. Kevin, don't laugh, you're Lex.
I'm not sure either.
Okay, so we better now move on to chapter 24. We got to go back to chapter 22. All right, let's see, who is next? Ivy?
You
Wait,
just
hold on,
asked
hold on.
me.
Yeah, Kevin. After Kevin is Ivy.
You just asked me.
Yeah, what happened to my order? Did I just pass you? Yeah, I just passed you. Wait. Why you guys are jumping around? We started out with Helen and then William and Jessica and Ivy and Kevin again. Okay, let's see. Who is after Kevin? Max. You better save the day. Otherwise, everybody goes back to,
Me neither.
go back to punishment. Boy. Number 12, Sharona.
I got D because when the dirt prevents the shaft of the motor from turning quite rapidly, the back EMF has to decrease, and then using the
Why? Why the EMF decrease?
I'm not sure.
You're on the right track. Sometimes I just wanted to find out the reason, right? You don't want to just like what some of the other guys told me. That's just a lucky guess. All right. Well, the EMF is what? Proportional to the speed. Is that right? Do we still remember that? Proportional to the motor speed, right? So in this case, when the speed decreases, what happened? The EMF has to decrease. All right? Okay, so keep going, Sharona. You're on the right track. And then what about the current?
The equation for current is I equals to V minus the EMF over R. So if the EMF decreases, then the current increases.
Okay. It's not that tricky, right? If by definition, if we already know the EMF is proportional to the speed, and we given the speed decreases, right? That's given. Am I right? From the problem. Therefore, we know the EMF has to be decreasing. And also the current is given as V minus the EMF. Pretty much that means the voltage is going to be a constant at the socket. And then the EMF is varying, right? It's a variable. Now it's going down, it's decreasing. Therefore, R being a constant, then we know the I has to go up, right? The current has to go up, increases. All right. Okay. That's what, number 12, number 14. Wrong?
I think is B.
Say again?
B.
Okay. Any reason that you pick B?
Because
Hmm? What is the energy formula?
1/2 L I squared.
Okay. So in this case, what do we, I mean, in order to find out the ratio I1, I2, do we need to solve for I1 and solve for I2 and then figure out the ratio?
No.
Hmm?
No.
Say again?
No.
No? Okay, good. Why? If you don't find out I1 and I2, how are you going to find out the ratio?
Divide them.
Okay, so again, right? If you guys remember this is kind of related to the kind of SAT1 math problem, or sometimes even SAT2. When you ask find out the ratio, you don't have to dive in and try to figure out what is I1, what is I2, right? In this case, you are given what? The energy stored on these two are the same, right? These two inductors store the same amount of energy. Therefore, according to your energy formula, the first one is what? 1/2 L1 I1 square has to equal to 1/2 L2 I2 square. All right? So if you rewrite this formula, then I1 divided by I2 is equal to what? Square root of L2 over L1. Right? Now, what's the relationship between I1, L1 and L2?
L1 is half of L2.
It only has half of the inductance, right? So you can either represent L2 as a representation of L1, or you can represent L1 as, you know, what is this? L1 is equal to 1/2 of L2. Right? Either way, you can substitute with whatever the relationship. So basically it comes down to L1 equal to 1/2 of L2. So substitute either way, I1 or L1 or L2. You're gonna find out I1 over I2 is actually square root of 2. And that's how you got, you know, that particular number, 1.414. Correct? Okay. Anyone has any questions on that one? All right. Let's see, which number are we on? That's 14. What else we have? We do have another one, 18. Okay, so which one are we on? Wrong. Alan, 18. Alan?
Can you hear me?
Go ahead. 18?
I don't know. I just guess. I put A. I don't know if that's right.
Can you guys hear Alan? Can you guys hear what Alan just said? Hmm?
I guessed. I don't know the answer.
You guessed it? Wow. Everybody is so lucky today. How about Max? What do you think 18? Problem 18.
I think it's A.
Okay, what is your approach?
Because V, the first V is larger than the second voltage. And then according to Ohm's law, we can get the first resistance is greater than the second one.
Okay. Everybody else agree on that reasoning? What is, again, right? For that particular problem, what is given? What do we know? The current in resistor 2, let's say without the transformer, right, is the same as the current in resistor 1 with the transformer. Now, in either case, the current is always equal to voltage over R, right? And then the voltage, the resistance, we all know. Now, since the transformer is a step-up transformer, therefore the voltage applied across resistor 2 is going to be smaller than the voltage applied across resistor 1. Do we agree on that? Is that clear? Yes? No? Okay, so everybody okay with that, right? And then the smaller voltage across resistor 2, that's going to lead us to that is going to let us know, or I should say, lead us to the same current, because the greater voltage that need to cross resistor 1, that's only because R2 is smaller than R1, right? That's the only reason that we would arrive, say, oh, across R2, there's going to be a smaller voltage. Current being the same, a bigger voltage would give you a bigger resistance across the voltage, across the resistor, right? Do we see that? So the important thing is derive the current in 2 and 1 has to be the same. And then use the I equal to VR, V over R, would be able to figure it out. That would happen, a smaller voltage across resistor 2. That's only because resistor 2 is going to be smaller than resistor 1. Okay? Now, also, let's see. I think last time I was informed by the class manager that we typically have a once a week, like online Q&A session going on Sunday. Are you guys aware of that? You know, some kind of a TA help session going on Sunday. I believe it's from, don't quote me on this. I think it's from 10 to 11, which is posted on the Google Classroom before. I don't know, did anyone use that meeting before? Or use that session before? Yes, no? Okay, so just in case you have any questions that you wanted to ask or going through. Oh, sorry, I just saw a message. Hold on. Oh, okay, somebody is not with us today. Okay. Is that a good time? Would you guys be able to make it? Because that was the time that was given to me. So I don't know, like how many of you guys will be able to make it if you will have to go ask questions on I believe Sunday, right? You guys want a Sunday morning or Sunday afternoon better, or what do you guys prefer? On that particular session is okay, time wise? No response. Oh boy, you guys don't have any preferences. All right, so most likely that's going to be the time frame then, if nobody has any objections. So feel free to get online and to use that particular help session if you wanted to have some question answered. I believe that one also has some kind of Zoom ID and the password provided. So access to the Google Classroom type, right? They should be able to, should be already outlined over there. All right. So, all right, let's move on to, boy. Now everybody has a copy of chapter 24? Yes? Sure, right? 24, where's my 24? For some reason, we were asked to skip 23. So then we go directly to chapter 24. Now, in this case, I also made a chapter 25 PPT available. So it's all going to be on the Google Classroom in case somebody wanted to, well, not just somebody, highly recommend everybody to read up on it ahead of time. Chapter 22 is a little bit, confusing, right? But if you read the textbook and see how the formulas were derived, you should be able to handle this pretty straightforward, I would think. Okay, so if we are not 100% sure on some of the concept and to applying the formula, I would recommend go back and combining the textbook for chapter 22 with the PPT on chapter 22. All right, so, and also, I think I always said I'm going to give you guys ahead of time, but only one day, maybe it's the same day. So that's kind of short. I learned my lesson as well. So this case, we're going to make the chapter 24 and the chapter 25 PPT available, right? So you got plenty of time to read it ahead of time. Read up on the textbook as well as the PPT, just so that some of the fundamental stuff is not going to get lost in the shuffle. All right. Okay. Anything else from chapter 22? All right. Just on a separate note, last time I think I asked you guys, any of you guys have a dog at home? Zero? Wow. None of you guys? That's interesting. That's very interesting. Especially during the pandemic, it's supposed to be, you know, a lot of the dogs are going out to different families like hot potatoes. So, all right, now let me share screen with you guys. Okay, you guys can see that, right? Everybody see that? Boy. Trying to figure out what is the best way to do the camera and this. So you guys can see the PPT without the zoom, the headshots of the zoom blocking the material. Okay. Okay, so when you connect to an AC generator through wires, you will be able to create a electromagnetic wave, right? And then the direction of the wave traveling is a little unique. It would be what? It has to be perpendicular to the field, as well as the magnetic field. That's what I mean. Wave is traveling in this direction. Okay. And then the magnetic field is this direction. And the E is pointing that way. So if we use a 3D picture, this is what's going to represent. You have your B going this way, E going that way, and then the wave is traveling in the X direction. Okay, B is in Z direction, E is in Y direction. And then speed of light in the ideal situation, in a vacuum, is equal to this. Okay. Okay. Now, once you have this so-called antenna wire, right? You have the two wires that's going to be parallel to the electric field. Then you will be able to detect the radio wave, right? That's going to be going through this type. Now, obviously, you need to have an amplifier to receive or say to detect that particular audio for the radio file. But that's the basic idea, right? You have the antenna wire, you have this circuit made it in such a way that for the wave to travel in here, you will be able to detect as an output. So you can also do the rotating of the loop, right? If it's moving, if it's changing, you will be able to have output. Spectrum, obviously we have a visible ones and we have the invisible ones, right? Certain things we can detect with our naked eyes within that range. But all in all, as we can see, that frequency, that band is pretty small. Okay, so in terms of wavelengths, in terms of the frequency, it's only a portion of the light that human eyes can detect. And many a times, you know, whether it's the AM, whether it's the FM, whether it's the microwave signals, we won't be able to see or detect through our human eyes, right? So some of these are used for medical devices. It will be able to give us a better idea, but that's typically how they're going to be stacked up in terms of the magnitude, in the order of, say, you know, to the how many power, you know, you're talking about wavelengths, or you're talking about the frequency, which is going to be in hertz, right? Wavelengths is going to be in meters. So now how we're going to figure out the wavelengths? Anyone remember? Formula-wise? Now, we already know the frequency, right? So that's, let's just say visible light is going to be in between this much range in terms of frequency. Now, what about the lambda? All right, what is the wavelength in range? Okay, so always equal to what? The speed of light equal to wavelength times frequency. So from here, we should be able to figure out what is this. The smaller the frequency, the bigger the wavelength. Okay? The reason being, C is equal to wavelength times frequency, right? So it's inversely proportional relationship. So if this one is big, then we know the frequency has to be small, and vice versa, right? If the frequency is big, then we know the wavelength has to be small, right? That's the only way to come up with a constant. Any questions on this? And also we introduced the diffraction of the AM radio wave and the FM radio wave. What does that mean? That means, oh, hold on. That means when we have a wave permutating, and if we run into, let's say, a building or any kind of obstacles along the way, then the wave will be able to bend it or lose certain power and yet still going through. Okay, so, and based upon our formulas, we should be able to calculate and say, okay, if the speed of the light, right, is going to be a constant, then which way are we, say, should be able to bend more? Right? Have you thought about that? Okay, so we'll keep going. We will come back and revisit this a little bit more. Now, example number 3 deal with what? Supernova. What is that? That's a violent explosion, right? Everybody heard about it. Okay, so what does that mean? That means it's an explosion of certain stars in the universe. Now, why they say viewing this is like looking back in time? What is that? I mean, anyone wanted to offer a common sense explanation? Yes? Common sense, right? It doesn't have to go into specific physics. What does that mean, looking back in time? Anyone?
Because it takes time for the light to travel to our eyes.
Okay. All right. And oh boy, I can't see the name now. That's weird. I should be able to see the name here. Now, is it Helen? I see you raise your hand. Is that rare? I don't have the name on the screen, so I gotta guess now.
No, I wanted to say it, but Steven said it.
Okay, so similar, right? So if you or anyone observes this through some kind of, super telescope, you're actually watching something that happened probably a long time ago, right? Not instantaneous, right? It's not like we're watching some kind of live TV event, then we know that's within fraction of seconds, right? It might be some delay, but not gonna be that much. But if we're watching this could be millions of light years away. I don't know, whatever the distance, right? So like Helen and Stephen mentioned, even though you're watching this through your super telescope, that could have happened a long time ago, because it takes time for those explosions, for the lights, and travel back to you, right? Back to your eyes when so in reality, this is something that's probably happened a long time ago, based upon the distance, right? You can figure it out exactly how long that's going to be. All right. So does that make sense to everybody? Or you guys are just not willing to say your 2 cents? Prediction. Okay, so Maxwell, that's his prediction. That's how he came away with calculating the speed of light. All right, and we will take his word for it. Okay, so that's the formula to calculate. When we talk about, electromagnetic waves and this and that, and microwave would be a good example, right? We all know how convenient it's going to be, and the reason being, this electromagnetic waves actually has energy, right? That's why you got a cold piece of bread from the refrigerator, you can microwave for a minute and a half or whatever it is, boom, it's ready to go, hot and toasty. Okay, so where did we go? Total energy density. That's another formula that we need to be aware. So when we do the lights, it's related to these two constants, right? And then when we do the total energy, as we can see, it's going to be this plus that. Different calculations, right? So, and also the energy carried by this particular wave. Particular energy divided by the area, right? The total energy divided by the area, that's going to give you this. And how are we going to calculate the total energy? This is what we have, right? We have the volume times U. So if you carry that through here, this is the formula that you got. We'll take a closer look at this. Okay. Section 5, Doppler's effect. Let me take a look. We have total of 9 sections, if I remember correctly. Oh, okay, it's only 6. Wow. Okay, we'll stop at 4. All right. Come back in 10 minutes, take a break, and we'll go back to our textbook to take a closer look at this. All right, so feel free to go, walk around and grab a bite or whatever. All right, we'll come back in 10 minutes. All right, everybody comes back yet? Jeez. Steven is the only one turn the camera. All right, everybody comes out of your hiding. Nice break. Now let's resume. We have everybody back. Room. Everybody's back except Room. Emily.
Emily says she's in the restroom.
All this time? That seems okay. Yeah, Ron sent me a private chat message, so Ron is excused. All right, let's take a look. Now, it's probably easier for me to just share screen with you guys. Okay, let me minimize the picture a little bit. You guys see the picture, the Zoom picture, or just the textbook? Tell me.
Just the textbook.
Just the textbook? Nice. Okay, cool. Yeah, I don't want the Zoom picture to block the material. Okay, for now we can minimize this. So you guys can see it, right? For some reason, we didn't cover the 23 for chapter 23. I don't know why, from the syllabus. Excuse me. So we move right on to chapter 24, which is deal with the electromagnetic waves. So first concept, right? We deal with the speed, right? The light, speed of the light. And further down, we'll be able to figure it out, say, okay, hold on. Can't move. The speed of light is given in such a formula. And then this is the electric permittivity as well as the magnetic permeability. Okay. And that would give you the speed of light in vacuum, in that surrounding. Now, we all know through different substance, through different density, speed of light might varies. Okay, so for this particular formula, this is given in vacuum, right? The speed of light in vacuum. That's what we need to keep on, make sure we remember that. And also from the PPT, we didn't give you a clear or say detailed enough information. When we talk about the energy density of an electromagnetic wave, that would gonna be the overall energy divided by volume, right? That's gonna be the density. Now that also is given by such. Now we all know what is E. That's the magnitude of the electric field. And what is B? That's the magnetic field, magnitude of the magnetic field, right? For this particular wave. And also you can do this, say, okay, from here, what do we know? Well, if the electric and the magnetic parts of the total energy, they're equal, right? Because it's the same wave, then you can do this. You could, because it's half of this, right? You can say, okay, then the total is going to equal to that. as well as equal to this, right? As we can see, this is 1/2 of the constant times E squared plus 1/2 B squared divided by this constant, right? The magnetic constant is going to be not magnetic constant. The magnetic permeability, right? That's the that's the terminology. And then the electric permittivity, the beauty of the English language, right? They have different words for it. So if these two are equal, then we know we can rewrite this as twice as much this as well as twice as much this, right? This one is related to the electric part. This one is related to the magnetic part. So with these two being equal, then you can rewrite the energy E is equal to C times B. Okay, do we have any questions on this? You said, where did C come from? Huh? From here. Right? Everybody agree on that? So when you have this one equal to this one equal to this, what do you got? You actually have this term equal to this term. Right? And then if you do the, math manipulation, this is what you got. Now, obviously, we don't have to worry about the positive and negative value, right? Because this is all considered as positive value, right? So you can just, square root of E is equal to this. Okay. Any questions on this? Because I can't see your picture. You gotta just say it. I minimized the Zoom picture right now to see the textbook. So if you have any questions, just say it. All right. You don't need to raise your hand and all that because I can't see you. So far, so good. And then the next step, remember the previous chapters, we deal with the RMS, right? The average value. So in this case, it's the same thing. I would say it's a similar approach. When we deal with the average value equal to 1 over square root of this, and for the average value of B is equal to 1 over square root of B0. All right. Now, therefore, in the end, the intensity is going to be related to the total energy density according to this equation, right? So that relates the intensity is going to be equal to the speed times energy. All right. All right. So with that in mind, let's go back. Use the right-hand rule, we should be able to determine the direction of the, right? They say the oscillating current in the antenna is going to create a magnetic field that point P that's tangent to the circle around this. And also, this is directed when the current is upward. So if the current goes the other way, then what do we know? Then for this particular field, is going to be going in opposite direction, right? If the current flips, then we know the magnetic field created is going to be opposite direction simply because the current is opposite direction right now. Okay, so again, that's where we got it from the right-hand rule can indicate that. So when we have this particular wave radiation field far from the antenna, right? It's radiated, it's moving away from that way. And then the E and B field are always going to be perpendicular to each other, as well as the direction of the wave traveling, right? So electric field is going this way, right? In the Y direction, magnetic is in the Z direction, and the traveling direction for the wave is X. Okay, so they are all perpendicular to each other. Speed of light, we know the calculation, as well as the, what is that related to the, oh boy, permeability and, oh boy, forgot that word. Anyone can help out? What did we talk, what did we just learn? Permeability and what is the other one? Don't remember? You want me to go back again? We just saw the formula, remember? So what do we have? You guys can see the textbook, right? So when we deal with the magnetic, it's the permeability. When we deal with the electric, it's permittivity. Oh boy. So permittivity related to electric. Permeability is related to magnetic, right? It's easy probably connecting these two with the different constant, right? As you can see. So this one is related to electric. This one is related to magnetic. Okay, different words, different constants, right? Now, they're all related to speed of light, right? So from here, that's where we derive the last formula from. All right. Yeah, let's not go any further. So this is where we at. Going a little bit further up, wavelengths of the sea, right? Or visible light, right? We did a little bit of that example earlier. What is the visible light range, right? And that has everything to do with the wavelengths, because the C is going to be a constant, right? The bigger that you have for this, the smaller that you have for the frequency, right? The bigger the wavelengths, then you know the frequency has to be small, because constant is equal to this times that, wavelengths times the frequency. So this is the direction that we didn't actually go in further, right? So when you have an AM wave and an FM wave, right? What types of wave would you expect to bend more readily, such as a building? What do you guys think? Without seeing the answer, right? Just common sense. We all know what happened to the FM radio wave, what happened to the AM. Typically, right? Correct me if I'm wrong. Typically, the AM wave travels further, right? And then in terms of the interference, you should have lesser interference when you're trying to listen to an AM radio, some kind of AM channel. When the FM channel, it's easy to be disrupted you know, when you have a building or something blocked, right? So in this case, whatever is going to be the longer wavelengths, that would bend more comparing to the shorter wavelengths. Does that make sense? Yes? No? Therefore, when we deal with AM radio waves that has a greater wavelength, then they tend to exhibit greater diffraction, meaning they can bend more around certain obstacles along the way. All right? Okay. We touch upon speed of light in vacuum and so on and so forth, and also looking back in time, how long did that travel, right? The distance wise, right? So travel time, distance divided by the speed, that's going to be, what is this? Seconds, right? Wow. Holy smoke. Wow, we're all going to be perished. As you can see, that was 175,000 years, right? Whatever we see, if we're lucky, you know, through those super scope, that happened long time ago, right? As we can see, simply because the speed of light it's just way, the distance wise, right? Light years, how many light years away? That's super crazy far, right? So and also Maxwell's formula, right? Electromagnetic waves. These are the constants that, you know, should be given, right? For certain, you know, back in chapter 18, if we still remember, right? So, and that's how we carry through and got the calculation. And for chapter 21, we figured out that one, the other constants, magnetic constants, right? Related to this. So, and then the energy formula, density. What does density mean? The definition of density is total energy divided by the volume, right? That can equal to this, or that can equal to that. Now, for the magnetic density, that's equal to this as well. Now, what is the total? Well, total density should be this one plus that one, right? Now, if we know, or say, if we know the magnetic field and the electromagnetic wave, when they propagating through a vacuum or through air, this and that, they carry the same amount of energy. If that's the case, right, we talk about the density, right, the energy divided by the volume, and they happen to equal to each other, then we can rewrite the energy as such, right? Because originally it's only 1/2 plus 1/2. Now we can say if they're equal, the electric and the magnetic, then we can rewrite the total energy as such, right? The density wise. And as well as replacing half of this with this, right? Twice as much of this, right? That's basically what it comes down to. It's supposed to equal to this electric plus magnetic. If they happen to be equal, then we know we can rewrite this one as, say, twice as much this. We can rewrite this one as twice as much this. And that's how we derive these two formulas from. And then if we equal these two, right? If we go back to the speed of light formula, which is related to these two constant, right? You can say c squared, right? If you square root of both sides, then you're gonna have c squared times this times that equal to 1. Is that right? Then you can plug back in here when we have these two constants, and then wind up with E equal to this. Are we okay with this? We see how we derive from here to here. And then when we deal with the root mean square, then that means it's always going to be 1 over square root of 2 times the maximum value. This one is always equal to 1 over square root of 2 times maximum value. Okay, so examples. Let's take a look at the examples. The sunlight enters the Earth's atmosphere with this RMS value equal to this. Right? We need to find the average total density of the electric as well as the magnetic. Okay, so if we rewrite this, we got a new formula, right? Which is related to each other, right? Because this one equal to this one equal to this, and also we can rewrite the energy formula based upon here. Then what is that related to? The B as well as the E value divided by the speed of light, right? Are we okay with this? From here, right? We can see that. So you say, what happened to the square root? Well, this one has a square root, this one has a square root. They're going to cancel each other. Do we see that? Therefore, you still wind up with C times B root mean square is equal to E root mean square. Okay, so that's why when we do here, we plug in the number, this is what we got. Once we know one of them, then we can figure out the other one. Okay, are we clear on that? Right, because the original formula given E root mean square value, then using that, we should be able to figure out what is U. Okay. Do we see that? Are we okay with that? All right. So because we need to figure out the average density, right? The average is going to be related to the root mean square. Okay. So that's how we got this equation. And then the magnetic field root mean square, what is that related to the electric root mean square? That's where we got from here. Remember the square root, 1 over square root, 1 over square root, they cancel each other. So it's still going to remain the same. Okay. Any questions on this particular example? All right. And also, when we talk about the power intensity, that's another concept. Where is that? Where is that? Blah, blah, blah. Definition of intensity. All right. So when you move through space, it carries energy from one region to another. The energy transport is characterized by the intensity of the wave. Now, let's say we enter this in sound waves, right? Do you guys still recall? The sound intensity is the sound power that passes through perpendicularly through a surface, right? You got to be perpendicularly. Now, for the intensity of the electric magnetic wave is defined similarly, right? This one got to be through the surface area. Therefore, if we do the intensity, that would equal to the total energy power through that particular surface area, right? Whatever the surface area, and we need to divide it by that, right? So this one equal to total power divided by the area. Now, in this case, you say, where do we have, well, why we have that? Well, intensity is equal to what? The power is equal to what? total energy divided by the time, right? So if we substitute that, total energy divided by time divided by area again, this is what we have, right? So, and also we know total energy is equal to total energy density times volume, right? So this is the total energy density. This is the volume. And that's where we have the intensity representation. Okay, so it's going to be related to the speed of light as well as what? U. All right, and then we can substitute what is U? Well, U we already know is equal to, remember this formula, right? Early on, this one is equal to this, right? Or we equal to 1/2 of this plus 1/2 of that. Okay, so if we substitute in here, this is the formula that we got. And then if we simplify, this is what we wind up with. You can either express in terms of the electric as well as the constant, or magnetic as well as this constant. Okay. All right. Power and intensity. Yeah, let's this is a 5 already, section 5. No, let's just stop right here. Let's just stop at section 4. Let's go back and do some practice problems. Let's see where we are. Where's my book? All right, everybody, turn to page 763. Yeah, 762. Let's do 1, 2, 3, right? Easy enough for the concept problems. Okay, so 1, 2, 3. All right. All right, you guys still working on it? Anyone done? All right, let me get the homework first. So 8 problems. 1, 2, 3, 4, 5, 6, 8. Yep. And we will come back on Saturday to go over the concept problems first, and then wrap it up chapter 24. Okay, so like I said, make sure you read it ahead. All right. So any question before we let it go? Code it off for the day? Anyone? All right. I'll see you guys Saturday. Okay. All right. You guys take care.
Thank you.
You're welcome.
question.
Yes, Alan, can you speak?
Uh,
I can barely hear you. I can barely hear you. I can't, you know what? Turn the camera off. Maybe that helps. Otherwise, I can't hear what you're saying here.
Okay, is this better? Hello?
A little bit better, yeah. Can you turn the sound up a little? Or closer to your mic?
Yeah, I'm gonna get through. Is this better?
A little bit? Yeah, go ahead.
Okay, so for 9 on the focus concepts on last chapter 22.
Yeah, what about chapter
The
22?
one, number 9, focus on concepts, the one we covered.
I still can't hear you.
Number 9,
Uh-huh,
on focus on concepts, the
right.
one we covered in class. How do you know that the outer coil is, how do you know the magnetic field of the outer coil is going into the paper?
It's a little bit of in and off again. You say, how do I know the
I'm
bigger coil? What about it?
Look at the chat. I typed it. Hello?
How do you know the outer coil, the magnetic field is going into the paper? Okay, so where is number 8, number 9, right? Okay, so what do you know for sure? When you close the circuit, right? What is your right-hand rule? Where is the current flowing? Hmm? Can you hear me?
I'm typing in the chat.
Well, I see your question. Yeah, I can hear it now. I think turn the video off helps the quality of that.
Do I look at like the voltage thing? Because I don't know which way the current flows.
Okay. Okay, when you close the circuit using right-hand rule, and you know, well, actually, you don't need the right-hand rule. You know the current begins to flow counterclockwise.
Why? Why do
Why?
you,
Because when you have, where is the positive terminal?
I'm not sure.
Whichever is the longer one. All right, the longer one is indicating the positive terminal, the shorter one is indicating the negative terminal. Therefore, the current is flowing from positive, going through the circuit and into the negative.
Okay.
Counterclock.
And then you right-hand rule, right?
Well, you don't need right-hand rule because based upon the graph that was given to you, right? If you take a look at the graph, what do you got?
What graph?
Well, the problem.
Oh, the drawing?
Yeah.
What was your question?
No, it's not my question.
Oh,
Look
no.
at the graph,
Yeah.
right? When you close the switch, where is the positive? Where is the negative?
The positive's on the right. I get
Yeah.
that it's going counterclockwise now.
Right.
So how would you use right hand rule? Because I thought for the second right hand rule, you point your thumb in the direction of the current, but this time the current is like it's circular.
Okay, so you can either do that, or you can finger curl, and that would give you the indication of the direction.
If I curl my fingers counterclockwise, wouldn't that point up?
No.
If I curl my fingers counterclockwise, my thumb points up, doesn't it?
What is that?
That's the magnetic field.
Correct. The field, it's pointing towards you. Correct.
Yeah.
Okay.
Okay.
And then what about Lenz's law? The induced current in the smaller one, where is that direction? That's going to be opposed to the field of the larger one.
Okay. Could you
That
explain
means-
how Lenz's law works again? I don't really understand why it's opposed.
Well, that's, if you go back to the Lenz's law, whatever the induced current is always going to be acting in such a way to counter whatever the original movement or the original field, right? So if you talk about the larger coil is pointing towards you, then the induced current in the smaller one must be opposed that, which means it's going to be going away from you.
What happens when let's say initially the switch is closed and then you open it? Then what happens to the induced magnetic field?
Well, if it's open, then there won't be any current flowing.
No,
in,
it
right?
starts off closed and then it opens. So like the current decreases.
Well, it's going to be dropping to zero, right? From
Yeah.
whatever the value. Therefore, it's always going to be induced by the bigger one acting on the smaller one. It's going to be always opposite the direction of the original value.
Always opposite?
Always opposing to that particular value.
For one of the problems I did in the homework,
Mhm.
let me see if I can find it really quick.
All right, you know what, Alan? Because I got a meeting scheduled after this class, so I can't stay here too long. But what I suggest is definitely using, would you be able to make it on Sunday?
Yeah, I can, but the problem is we have like another class on Saturday and I have like more questions. Can I just email you my question or do you not want me to email you?
That's fine, that's fine. Just send me an email. I deal with this later. How's that?
Yeah, that's fine. Thank
Okay.
you.
All right, sounds good. All right, see you Saturday.